So,
thank you very much. So we shift gear a little bit today. So I'll present work done by Maximilien de Breton and Daichi Kuroda, and together with my colleague Matthias Grossgrosser at EPFL. And what I'm going to talk about is it's essentially a non-supervised learning problem, which is well known to everyone. It's a basic building blocks, I would say, of many algorithms that look at a massive amount of data, which is clustering. And clustering means essentially that you partition the set of data. I call them items or objects in an ensemble X into clusters according to a similarity or dissimilarity measures, so that this similarity, pairwise similarity between two items, is large within a cluster and is, of course, low or small outside between two different clusters. And this similarity function, so that I'm going to use as supposed to be known, essentially it has two of the three axioms of distance in it. So essentially, similarity between an item in itself is strictly larger than between any other items. And of course, it's a symmetric relation. And you can use, I would say, the complement, the opposite, the inverse of that, which would be a dissimilarity between X and X prime. Now, there are many well-known, well-established methods about clusterings. Typically, the one that are the most popular are spectral clustering, or the one using modularity or greedy approach, so that Louvain, Leiden, Paris, they all wear the name of a city where the team that invented them is located. But my goal here is to work with clusters at different resolution levels. So essentially to look at the hierarchy from, so I assume that there is a clustering algorithm that finds clusters at the lower level, and I want to see if there are clusters made of different clusters. In other words, if there is a hierarchy of different clusters here. And so here, typically what you would have is so that's typically a motivation would be what would happen with, hope it settles now, with a data set, for example, high school data sets in which you would just cluster classes and so on until the root, which would be the high school just there. Okay, and so traditional methods produce in general binary tree almost systematically, and so I'm going to illustrate how they work. So how do you work? Well, you have your similarity function, so you look at the two objects which are the most similar to each other, X and X prime. Okay, so you list here below all the different objects, okay, that are here. You find the two most similar objects here, and then you pair them. And so you go bottom up this way. This is for the first two objects. Then you do the next one. And this procedure is called linkage. So this is what would happen, for example, for the next two. These two in green would be merged together. So these are the two items here. They are just merged together, and you continue like that. Now, when you do that for different objects, you have a similarity function which is defined between the pair of above objects, and you need to define if, say, you want to group together that green cluster with some other node, you need to pair these two, these clusters, this green cluster with another node, for example, this one, another object. You need to define a new rule to say what is the similarity function, so what is the value that you gave to the cluster itself. And this is called linkage. So the information that you have on this cluster here, you can say, well, I take the average of the two values I had for each of the objects, or I take the minimum, or I take the maximum, or I take any other linkage methods, rules to do this association. And so there are plenty of such rules. These are like three of the most popular one. So minimum, average, and then there is also different way to compose this average. For example, the word is a more complex expression like this. And so this defines essentially for the cluster what is going to be the new state, if you want, of the cluster itself. And this way you can progress and build completely the tree. And so when you do that, you arrive to just a tree. Now, this tree, because you each time merge two objects or a cluster and another object, will inevitably result in a binary tree at the end. Okay, and so all these linkage methods are binary trees. Now, clearly, you might have many different trees. You might not have a tree at all, a star, if there's no hierarchy at all between your objects. But if you apply any linkage like this, you will come with a binary hierarchy. And so that's the problem we wanted to address, was to go beyond this limitation of binary trees. So for example, if the similarity matrices are these two matrices, on the first one is very clear that you have two main clusters, and then inside the two clusters, you have similar clusters. In the bottom one, there is no hierarchy at all. It's flat, right? Each of the elements here. So if we have the true hierarchies between the items, this would be the one I would have for both of them. If you apply linkage, a very likely outcome for the first one is this binary tree. For the second one is this binary tree, which actually is exactly the same. Okay, so it does not capture the hierarchy that you have in the data at all, just by construction itself. And so that's an issue that you have with whatever linkage rule you do, if you do a bottom-up method like this. Okay, so what is the solution? Well, the solution would be to remove some of the clusters that should not be there, that just artifact of the construction that you do with this binary construction. So for example, if you look at the first one, you see that on the left branch, fortunately, I don't know if there is a pointer here. Yeah. So here, this one, for example, AB, should not be there. Okay, so I should remove it. It's not a valid cluster, essentially. This is, and so if I do that, okay, I remove it, and I do the same for the bottom one, then I arrive to the true hierarchy. Okay, and so what's the rule that I should apply? Well, the rule is actually quite simple. It's what was already put forward in that paper from 2014 as a good cluster. Essentially, what you want is that you declare a cluster to be valid if within the cluster, like the blue circle that I have just here, all the similarity between all pairs of objects within the cluster is larger than the similarity with an object outside the cluster. This is the rule I'm going to put forward as declaring that the cluster is a valid cluster. So if this has a property, then indeed it's a valid cluster according to my similarity function, just S. Okay, and so if I have a tree, a hierarchy that only contains valid clusters, then I call it a valid hierarchy. This represents something which is in the hierarchy. Now, there might be multiple such trees. Indeed, if you think of the star topology, so all the clusters connected to the root, it's a valid hierarchy. All the clusters, all the points are clusters. I don't put any fake, if you want, any wrong cluster in the tree. So it's a valid hierarchy. Of course, it contains very little information. So I miss most of the big clusters in the tree. And so I have something which is not, I would say, the maximal element that I could have among different hierarchies. So what I would like to go is not to have this, but to find hierarchies that offer more insight into the hierarchies that I have in my data structure. And so the first thing we showed is that trees with different, so they define essentially a partial order, but this partial order has a maximal element. So there is one hierarchy, essentially, which is the largest one, which contains all the possible valid clusters that you have in your data. So essentially, all the clusters are there and only these clusters. So it's an object which is well defined. There's always a hierarchy that you can construct using that. Now, the fact that it exists is a good thing. How do you find it is the next question. And actually, what I showed just before was the idea to do. So to follow. So the first step I will follow is the binary linkage. So if I build this, I will construct this binary tree. And in this tree, I will have some clusters, some nodes there of my tree that are valid clusters, that are true clusters in the data. Another, the one that I have in red just here, which are invalid cluster, which I should remove. And so I check if in a second stage, if I should remove or not these clusters. In other words, if a cluster that do not satisfy for all the elements in the cluster this inequality, I just trim them from the tree, and then I arrive to this tree T hat. So this tree T hat has only valid clusters, because I've removed by definition all the other ones. So it represents a valid structure of the data. Is it the maximal element? That's the other question. So don't we trim by doing this other cluster that we should not have? That's what we are going to see in a moment. So essentially, if I apply this to the algorithm, I arrive in these two cases to the true hierarchy. Now, these are easy cases because you see the clusters are very visible in the data. If I take situations in which clusters are a little more blurry, so essentially it's not clear which clusters I have are valid, which one are not valid, and I apply the same kind of algorithm, it's not clear that necessarily this tree that I have obtained is the maximal tree that I could obtain for all the hierarchy. It's a valid hierarchy because all these clusters here are indeed true clusters, valid clusters in my data, but is it the largest one? That's still to be seen. And so that's the by construction. So the question that we have is whether it contains all the valid clusters. Right. Voilà. Okay, and so to remind you, so I have the most informative hierarchy. That's the one that contains all the valid clusters and only the valid clusters. So it's the largest valid hierarchy. And the second theorem we have is that if the linkage rule satisfies some conditions, so it does not work for all linkage rules that I've presented earlier on, then indeed this algorithm just produces the most informative hierarchy. And the idea is to see what kind of proofs we need to have. The proof is as follows, when the sketch of the proof. So imagine that at some stage, I have this valid cluster here in blue. Okay, so it means that all the objects inside the blue circles have a higher similarity than any object outside that blue circle and an object inside the blue circle. So that's why we have a valid hierarchy. Okay, and imagine that earlier on I had all these other clusters that were just before. If I want to say pair, I find that the similarity is the highest between these two clusters, one inside and one outside. Then I have an issue because I create a cluster there that I should not have in the trees. You see that there is an overlap. This will not correspond to a tree. I will have a cluster here in red that I should not have in a construction of a valid hierarchy. So the rule that I want to observe is that whenever I merge, I cannot cross the boundary of an already of a valid cluster. So that's the rule I need to have. So the red one should not exist. I can have, on the contrary, merging within the cluster. That's certainly fine if I have things like that. So the condition is to find what is the condition on the similarity function that ensures that mergers do not take place between cross boundaries of a valid cluster. And so that condition, if you work on, is very similar to the condition that defines a valid cluster, but so that's the one I have here. But the condition I had before was only between objects. This one is between clusters. And so I need to check how I can translate that condition here from the different objects. And this is where the linkage rule comes into action. The first iteration, that condition here is always verified if I replace the cluster by the object itself. So the bottom layer is always going to be correct just because of that. But then for the next iteration, I need a number of conditions. And these are conditions, for example, that ensures that the first condition over there is met. So we need to check if the linkage rule verifies these conditions. And if we come back to the different linkage rules that I had before, well, there are some that do and some that do not. So for example, the minimum and the average do verify this property. So they always produce, they always merge at any stage of the process clusters in such a way that the new cluster is going to be a valid cluster. But there are many others. The most well-known one is probably the Ward rules that do not always produce a cluster which is valid. And so if you apply this linkage, for example, in trimming the tree, you might arrive to this tree, which is clearly different from the true hierarchy that you have just here. So you need to be careful with the linkage rule that you apply to be sure that your hierarchy is valid at the end. Okay, now this works, and I would say contrary to all the talks I have given before, there's not an inch of randomness in what I have produced, because you are given the similarity function and you just construct it. But there is absolutely, the similarity function describes perfectly the similarity between the different objects. In practice, of course, I always have noise. And so if I add a little bit of noise, well, this is no longer true. So how should I modify the definition of what is a valid cluster? That's much more difficult. So essentially, instead of putting that the difference is here between the similarity between two objects within the clusters and an object within the cluster and an object outside the cluster is strictly positive, I gave myself a margin epsilon to make it large enough. And then if I am lucky, essentially, if the true values of the so the S hat is the noisy one, the S is the real function. If objects are separated sufficiently apart, and the noise, so the difference between the noisy version and the non-noisy version is small enough, then I will recover the tree. But essentially, that's what I have just now. And so, sorry, if we apply this to, so of course, to have ground truth, you need to apply that to models. For example, a stochastic block model, which is a hierarchical stochastic block model. Sorry, I'm too fast. Voilà. Then essentially, so if you have a true hierarchy, well, that few methods that you can apply. So there are two methods that we found in the literature, one from 10 years ago and one much more recent. And if you apply it, essentially, there can be big differences between the different results. You see, for example, that some of them produces hierarchies that are completely different. Actually, it's one layer below. That's why you have so many just there. But essentially, from the true hierarchy, and the rule is actually not too difficult. You just use your binary linkage and you trim by checking the valid clusters. If you have a linkage, which is a simple linkage, minimum, maximum, average, are the two linkages that work. All the other linkages that are more fancy usually do not verify the rule for always arriving to the correct result at the end. So that's what I wanted to show. We have still to work on the noisy case, in particular to deal with outliers. If you have just a single outliers, how do you handle it? And then we'd like to apply it to a number of settings. So I spoke of the hierarchical stochastic block models, Gaussian mixture models also, in which these are like canonical examples for clustering, in which we'd like to see how this works. Also in the presence of probability distribution, so to have the random aspect into.
Yeah. Thank you very much for the presentation, and I have a curiosity because all of this made me think about quantization. So the way I understood it is maybe because you were showing it in 2 dimensions, but you quantize once, and then you quantize the quantization centers with respect to these similarity measures, and so you build up your hierarchy. And so the question that came to my mind is, there is a link between your most informative hierarchy and rate distortion theory, or is this something that makes sense to look at?
Yes, I haven't seen anything that applies rate distortion theory in the setting of clustering, because so here you want to, yes, because you might have clusters that are very imbalanced, right? You might have very small clusters, large clusters. The hierarchy might be, so you might have a very unbalanced tree at the end, which in quantization often you would have something which would be more balanced if you, I mean, for most of the algorithm. Now here it's we call it most informative. It's just to give a name to this maximal valid hierarchy. I mean, that's the one, the one there. So there it's an exact result. So it's not, I mean, you couldn't say that I have some distortion. It's maybe in the noisy case that we could apply that.
Yeah, I think the thing that got me there is the definition, which is the definition of a Voronoi cell. So when you try to quantize and you decide the number of quantization points, then you have this algorithm that tries to find these cells.
Yeah.
And the cells might be sometimes very large and sometimes very small, depending on the distribution of points, which boils down to having these distances between the clusters. But so in quantization, you have the quantization point that appears at some point that you don't have in your model here. So, well.
Yeah, because the first layer, so the clusters themselves, the objects, that's done. You can use whatever your preferred methods, and then we start from this point on to the year.
Okay, thank you. Can you throw it?
So very quick, and maybe a completely stupid question, but as you were going through it, and I was wondering if you have a constraint that limits the number of points that you can have in the cluster, is an easy way of generalizing the approach to even the definition that you have.
I think it's interesting to look at, because essentially you would define the valid cluster to have these two conditions. but I have no idea of what side effects.
Yeah, I
it
couldn't.
have.
Okay. All right.
I think that's another problem because it might not be so easy to do because so if you can split a valid cluster into two and you say, okay, I cannot merge them because essentially I don't want to have clusters which are larger than this. Yeah, I could see fair enough in the sense that at one layer I keep two. Basically, I introduce an additional layer. It's the next layer that they are going to be put together. Yeah, maybe that's what it would produce, right? You would have a binary tree, and then you would merge them in such a way that so you would have you would check if you can, so if it is a valid cluster, if it is not valid, you would remove it. But then you would have this other condition that says, oh, but if you cannot merge anymore if you have that many points. So
Right. I mean, I guess, yeah, the question was, sometimes it may not have been the right choice later on. You only discover that later on. That's why I couldn't see if there was an obvious.
Yeah, not clear because if it would, it might change something in the algorithm essentially. That how to do the two steps.
Okay. Thanks.
So thanks for a very nice talk. Very clear. I'm just wondering if there's any reason why this might not work on like where your data is text embeddings. So imagine, for example, you're trying to cluster app reviews by kind of the main thing that people would talk about. And so an app review is captured by a text embedding and can compute the similarity of those. But would any of your criteria, would it still work?
So essentially our starting point is you have the clusters. So if they are embedded in some space, the point, I mean, I already draw them basically embedded in some sort of a Euclidean space. Then you would take these different items. And so they can be nodes of a network. For example, HSBM, they would be nodes of a network. A Gaussian mixture model, they would just be points in a high dimensional Euclidean space. So then you would have these points embedded, and you need to have a similarity function between each pair of the items. So this needs to be given before you can apply the algorithm. So maybe the difficulty is the second part, is having a pairwise similarity between all pairs of points. In the Gaussian case, you have a Gaussian kernel, and that defines, so two points which are very close to each other are like, so if you have a Gaussian kernel on top of them, well, you will have a function which is the exponential of minus the distance to the square between these 2 points.
You define text similarity, but often there's a threshold. So some kind of cutoff threshold.
Exactly. Now, something which is hidden here, I think it's is that if your similarity function is 0 between many points, then you have a sparse function, then you cannot do much with, because similarity is 0 everywhere, so you cannot do much for that. So you need a function, I would say, that has a non-zero value, and you don't need to have heavy tail, but you need to have tails that are not 0. If you have something that stops, and so a very sparse model in which your similarity function is 0, then essentially you have 0 and 0. You are going to reproduce a hierarchy, but which is probably not very meaningful for what you
do. Thank you for the nice talk indeed. So yes, I have a question on so when you're in some Euclidean space, you could also use this descending chain approach, and then you would completely bypass this problem of binary trees. So I'm trying to visualize, I don't have the answer in my mind of
why this is a bottom-up and not a top-down?
Yes. What is the framework which allows, which makes that you've entered this problem in this setting with dissimilarities? And what is the reason?
So top-down versus bottom-up. So we looked at that before. So to see So here indeed, it's a bottom up. So you go from the basic level, you merge two, and you construct the tree going from the bottom to the top. What you could do is also look for the main two clusters or 3, 4 clusters, and do what going from the top down to the bottom layers. Is that what you-
No, it's not what I mean. What I mean, think of assume you are in Euclidean space,
Yeah.
and you could try to think of, then you have distances between every pairs, and you could look at minimal spanning tree, sort of, right?
Yes.
And so, or descending chains, like what we discussed with SIA, and then it's still up,
Yeah.
bottom up.
Yeah.
But it does not create things which are binary.
No, exactly.
And so what is and I'm trying to see, I mean, because you don't depart from Euclidean or distance, metric space things, but as soon as you have a metric space, you can avoid
exactly.
that by a completely different route. So that I'm trying to
No,
visualize.
it's an interesting point. We discussed with Maximilian a little bit to see a little bit how because here there is no we are just giving this similarity function. It can be Euclidean, nothing. I mean, it can be very different. Of course, if you you do the construction, based on distances, and that creates indeed clusters. So I would say the clusters themselves are the object we start with, and then if you want to build a hierarchy, you would like to. There might not be any hierarchy in the. So then essentially what you need to arrive is to say, well, there is no valid hierarchy. So essentially it's a flat. It's a flat setting. So to have really valid hierarchy, you need that the distances between some of these little clusters is much smaller than the distances between any of them and a cluster which is far away. And so my conjecture is that, like in your work with Say, you would have something which is flat. There might not be a hierarchy at all in this setting.
Thank you.
Thank you very much.